acceleration is Vf minus Vi over time. When do you have a negative acceleration is when your final velocity is smaller than the initial velocity. Just that. Final velocity is smaller than the initial velocity. Then you have a negative acceleration. Now let me ask you a simple question right here. When I throw this marker upward, as the marker is going up, is it accelerating or decelerating? Accelerating? Decelerating. Why do you say it's decelerating? Because it's slowing down, right? Okay. Now, while it's coming downward, is it accelerating or decelerating? So what is the acceleration at the very top? You said it is negative 9.8, right? When it's going up, it's deceleration. And you're saying it's 9.8 downward. What's the acceleration on the top?
0.
If the acceleration is 0 on the top, why should it come down? Why should it come down? What is causing that acceleration?
Gravity.
Simply gravity. Which way is gravity acting? It has to be always negative. It cannot be positive. Once it's off my hands, there's no positive acceleration because what is governing its motion is gravity, and that is downward. So there's no reason why it should accelerate at any point. Now, don't look at speeds. What is the definition of acceleration? Rate of change of velocity. Rate of change of velocity. That is acceleration. Not rate of change of speed. You get it? Don't define it as rate of change of speed. Then that's what confuses you. Oh, it's getting faster and faster, and therefore it's accelerating. No. Let me throw some numbers here. Let me throw some numbers. Suppose I'm throwing something upward at, say, 40 meters per second. So I'm throwing something at 40 meters per second. Since it is thrown up, is that velocity positive? Yes. What can be a velocity after it moves some distance? 30, 20, 10, and 0, right? So all through, as you look at it this way, as it's moving from here to here, is the final velocity bigger or smaller than the initial velocity?
Smaller.
Final velocity is smaller. So definitely it's a negative acceleration, like 20 minus 30 divided by the time it takes, right? So 20 minus 30 is a negative 10, so it's negative acceleration. Watch what's happening is after it reaches there, it's going to descend. So descending motion is this, that's 0. What is the speed here? What is the velocity here?
10.
Negative 10, because it's going downward. That's why I said initial velocity, final velocity, acceleration, and displacement, they're all supposed to be taken with care because it can be positive, it can be negative. Now, if you mess up on those signs, the whole problem is going to be messed up. So the best thing to do is take care of that. So when you say a velocity, immediately think about which direction is it going, and then put that velocity right. That is negative 10, and this is negative 20, and that is negative 30, and that is negative 40, so it reaches back at negative 40. So what is happening here? From here to here, is the velocity increasing or decreasing? From here to here, it is still decreasing. It was minus 20, now it's becoming minus 30, which means definitely this is smaller than this, right? So it is still decelerating. All through the journey, it is decelerating. And the graph that we ended up drawing for velocity time graph for something that is thrown up and it comes back to my hand is this. This is that instant where it just becomes 0 for a fraction of a second. That is the instant when actually it is crossing over that point. So that's the place where it is instantaneously at rest. It's not at rest for a long time. That instant it is at rest. Otherwise, you can see the slope of this line everywhere, even here. Even when it is at the very top, look at the slope of that line. that is negative, right? So in free fall, ignoring air resistance in free fall, what is free fall?
Falling that influence or anything? Except gravity.
Lacking resistance in fall.
Yeah, what is special about free fall? Special about free fall is an object that is in free fall has only one force acting on it, which is the gravitational force, the weight. Right now, is the weight acting on me?
Yes.
Then why don't I feel that free fall aspect? Because gravity is not the only force acting on me. There's a push from the floor on me, right? There's a push on the floor, and that's what makes me feel heavy. So why do you feel heavy? It's because of that push. The more you feel that push, the more heavy you feel. It's a feeling. It's just a feeling. So if you're heavy, then the push from the floor is also going to be equally high. And so you feel that weight. So if you put on 20 more pounds, immediately your leg starts hurting. Why? Because your leg is being pushed with a greater force now. That is what makes you feel your weight. As you lose your weight, you will feel lesser and lesser push from the floor. You understand? It's just purely that. Now, if there's no push from the floor at all, you feel weightless. But when you feel weightless, can you say that there's no weight acting on you? No. You feel weightless just because the only force acting on you is gravity. The only force acting on you is gravity. That's why you feel weightless. Now, my son actually, as part of the Yeovil medical team, he went to Florida. Yes. And no, Houston, and he was doing the zero gravity tests. So there's a big plane. They removed all the seats from inside. This is a special plane which does that. So they removed all the seats from inside. They got some brackets and all that fitted on the sides with belts or chains, belts that you can belt up to, so that you don't actually go anywhere else. And then this plane actually takes off onto the sea side. It takes off like that and really goes high, steep. And when it goes like that, accelerating, it accelerates so you feel twice your weight because it's accelerating upwards. And you'll see that in Newton's laws when you touch that chapter. It was accelerating like this. And after it's around 30-degree angle. So it accelerates really well, and then they kind of make the plane go down like this at 30-degree angle. But at 30-degree angle, they're accelerating really fast to match up the free fall. So you'll feel zero gravity. So when they're coming down like this, people inside experience free fall, which means what? Weightlessness. Zero gravity. And they were doing that around 40 times. So they used around 30 times for experiments. So what was the experiment about? Suppose there's a surgery that is supposed to take place in space. Suppose someone is not well. So if someone gets there and then somebody needs help, the surgery needs to be done by definitely another person. So it has to be done now. There's no chance of like bringing that person back here easily because they spend months over there. So if the surgery has to take place, will the blood flow? How will the blood move? And all those experimentations. That's what they were doing. And when are they doing the experiment? In that 25-second time. When it is experiencing zero gravity, that's when they test all that. And immediately before the time is over, they have to now experience 2G, which means twice the gravity. Imagine somebody else as heavy as you is sitting on your shoulders. You'll feel that. You'll exactly feel that. It will be like 2G. Not G, but 2G. So if your normal mass is like 160 pounds, it will be like 320. You will feel like as if you're heavy. So you may not be, like the moment you bend your knees, you'll be down. You can't carry that weight. You know what I'm saying? Like if you're locked knees, then you may be able to take the load. But accidentally, if you kind of bend your knees, you'll be on the floor. That's kind of, so it's dangerous. So most of them during that time, they kind of sit down or lie down and then there's a meter that actually shows what's the gravity. And then the 2g will change gradually to 0, and that's when they are floating. I've got a couple of videos about it. Yeah.
So if you were like in zero gravity to just like have something just resting there, would it have zero?
It is not zero gravity. Gravity is everywhere, even in the space stations.
Alright.
Gravity can never be zero anywhere. Gravity is never zero. It is the weightlessness that is caused by some effects. So it's a kind of what do you call, relative gravity is zero, that sort of thing. So when you say you're in free fall or you're in weightlessness, you don't have to be in space. You want to experience weightlessness, you can actually like jump off from the building. You'll experience weightlessness, like as if you are no weight at all. Don't do that, okay? So experience weightlessness for some time, but you know what? You won't experience pure weightlessness because air resistance. Because of air resistance, you will actually not feel that 100% weightlessness. And a little bit of that can be felt when you go over a road that actually is curving too much. We'll do that in circular motion later on. But if a road is curving like this and you go like that and come down, don't you feel that effect? You feel as if you're tossed up. That is almost partially weightlessness. So you feel like you're not gripping anywhere. So if it's the giant wheel, the Ferris wheel, right? When it comes down like that, you do feel a little bit of loss. Why? Because you feel as if the bench is not pushing you enough. Yeah, it is not going to push you enough because you are accelerating this way. You're not sitting on the bench just like that. So when you go like that, you feel heavier. And when you go like this, you feel lighter. And you feel that you need to hold on somewhere, otherwise you'll fly off. So that is, so the weightlessness does not mean you have to go to a place where there's no gravity. You can experience that weightlessness right here. So what they were doing was just going like that and making all those movements. And so there are times when it is like 2G, there are times when it is like zero gravity. So they get that zero gravity to, and in space station, you know, like there are a lot of instruments that actually work continuously because fluids. How do you get water? You don't take a stock of water for 6 months. First of all, it has to be lighter. You know, the ice cream that they eat, it is without water. I mean, it's dehydrated completely. It's like a crispy thing. It's very light. He bought one and brought it here also. So it was very light ice cream. And you open it, it is just like, you know, what do you call that? Some kind of wafer, right? And then as soon as you put it in the mouth, the fluid from your saliva gets in and then it just tastes exactly like as if you're eating ice cream. It's a weird thing. So light, but once you pop it, it actually is. So fluid is definitely going to be a big issue when you're spending a long time there because you can't take so much water. And whatever water you take is going to be sitting there, right? You can't throw it anywhere. So it's going to be in there, in different forms. So what they have is a machine that actually recycles urine. So the urine part of it goes into a machine that actually kind of does sort of a lot of filtration and stuff like that. And finally there comes pure water. Just go and drink that water. It's not just one person's urine, it's like whoever is there. It's weird to think about, but yeah, that's what they do. So there are machines that actually convert the urine. So whatever water you take is not going anywhere. So it's kind of recycled again and again and again, and you drink that. So this machine should be capable of working that way. So surgeries need to go on, and you need to clamp things, otherwise it will fly away. So your instruments, you can't just leave it like that, because they will drift off and go anywhere. And therefore they have to kind of bind it. So if there is a scissor or something like that, a surgical tool, you have to make sure that it is like sticking somewhere. It has to stick somewhere and then take it out like that. All right, so like Velcro is fine. So how these glues work in space, that's a kind of experimentation. So they did this experiment for around 30 minutes, and after that they just switched over to fun. And the fun time, my son is good at doing push-ups. Like at a stretch, he can do so many push-ups. He's right now in Detroit as an emergency doctor. He normally does push-ups, many of them. But then he was thinking, okay, let me see if I can do push-ups in 2G, twice gravity. So he was ready, and he could pull up barely. He just pulled it up, and then after that, while going down, he forgot the fact that he's still in 2G. As soon as he bent down, he just crashed on the floor. Luckily, he bent his head, and so he hit his head on the floor. The reason is because it's not like doing here. It is 2G. That means imagine another person of your same weight is sitting right on your body. And when you go down, it is not the same as how you do it here alone. That one. And this other experiments that he kind of did was he took his phone, and in zero gravity, his friend is across on the other side. He takes the phone and just gives it a push, and the phone goes like that. Absolutely straight, no bending anywhere. Just goes straight to the other person just takes it. That's a cool thing to see how the phone comes straight, no bending down. Yeah.
Is he able to follow rotation but continue to spin? And
Yeah, that's another thing that he did. What he did was he actually sat. He was sitting in a crunch. What do you call that? Crouching position, right? Is it like bent together and sit down on the floor like this? He sat down on the floor when it was 2G. He sat on the floor, and there was his friend ready. As soon as it became zero gravity, he's sitting on the floor, but he's like in zero gravity or free fall. So his friend just picks him up like this. He just picks him up like that and gives him a spin. And then he's just standing there and watching him spin right there. Very cool. I mean, someone who weighs 150 pounds and all that, just spinning like that in the air. And before the numbers go down, zero. Once before the number goes down, there is some kind of warning sign so that you better stop. So if you don't stop, you'll spin like that and suddenly, boom, on the floor. That will be bad. Yeah.
How do those things like carnivals where you're essentially pinned to a wall and they spin around and hold you to the wall? How do those things work?
We'll do that in circular motion. There are a lot of things that you will actually learn this year. You will learn lots of things. One of them is that thing is going to be covered in circular motion. It's a big chapter by itself, so I won't touch that right now. Because after I do circular motion, you'll say, yeah, I know why. I know what's happening there. Yeah.
So you said that everything has gravity, and I was kind of thinking about this. So, like Earth itself experiences gravity towards the sun.
Right.
Does the sun itself, as a whole, experience gravity, and towards what? Like, what is it? Gravity, like, what's pulling it?
The sun is basically what is in the middle of our solar system. Now, is the sun under the influence of some stars? Yes.
So it could be pulled. So that could be.
It is. They're all kind of mutually, offering forces, but it'll be very small though. Even though sun is big, considering the stars will be far away, it is going to be tiny bit only. And it's not from one direction, it's from all the directions. So it's a mysterious world we are in. So our sun is a cluster. Okay? Now, if you try to look further down, you'll see how the whole setup works. And that is just that's one system in our universe. And then similar systems are there, so many of them. And they're all like around each other like that. They form a kind of a sphere by themselves. Anyway, so the sun offers a force on the earth. That's what makes the earth go round and round. And because the sun is big and not too far away from the earth, when I say not too far away, for the sun, earth is not too far away. But for us, it looks like the sun is too far away. It is far away, but is not infinite. So the earth is under the pull of the sun continuously. The moon is under the pull of the earth continuously. So is the moon offering a force on the earth? Yes. That's what causes all those tides. So there are mutual forces acting back and forth. And unless you go far away from any of the stars and all that, then only you can actually have a zero gravity position. Otherwise, there is always a gravity that is coming into play. You get it?
If the sun exploded, what would happen with the gravitation of the planets?
Well, even if sun explodes, the center of that dust, the center of that is still going to be a center, the same center. So the center of gravity and all that is still there, and the mass is still conserved. It's not going to, whatever be the size of the sun, it's still going to influence us the same way. Yeah. Questions? Yeah.
If the sun does explode, wouldn't we die in that probably?
No, after 8 minutes, then we'll lose our light.
Alright,
Close to 8 minutes, you'll still enjoy sunlight, and after that, boom, it's all dark. Because the fusion reaction and all those things will come to a halt when everything just gets into pieces. Yeah.
Correct me if I'm wrong, but doesn't a supernova cause a black hole form?
Well, the sun
That is, again, a lot of theory involved there. There's a lot of theory involved there. So some of the theories are not proven yet, and there's nobody to prove that. So therefore, we just kind of keep them as theories and keep going. Yes.
So would like a human, would they exert gravitational
Say it again?
force? Like a human on something real small, they exert.
A human. Yeah, I have my own gravitational force. If I am taken to a place which is totally, totally far away in space, and I leave this marker like that, the marker will come to me. I am like a bigger body compared to the marker, so I don't fall to the marker. I will be moving a little bit towards the marker, but the marker will move more towards me because I'm bigger. It's like when you jump off, when you fall off from the top of a building, the earth is pulling you down, and you are also pulling the earth up. But the earth doesn't come to you because it is big. So the acceleration, it's both experience the same force. Both you and earth experience the same force, but who's going to be affected is of course you. So you go to the earth. Is the earth coming to you? Theoretically, yes. So that's why I said even if you go to remote space and when you release this, it actually will start floating towards you, because that's the gravitational force is the only force that this is affected by, and I'm creating the field. Anyway, we'll talk about that in gravitation again at a later time. Yes.
Is there a unit on Einstein's physics?
Unit.
Like there's like a chapter in the book.
Oh, you're doing grade 12. You're senior year. Yeah, in senior year we do quantum physics and atomic physics and all that. We'll talk about Einstein. Nuclear physics. Yeah.
Is it like a vacuum just increasing gravity? Or
Vacuum has nothing to do with gravity. Vacuum is simply meaning there's not a single particle inside there. That's it.
like suction. Is that like increasing gravity kind of?
No, suction. Vacuum is creating a suction because of pressure differences, and that is totally different. The suction that is caused can be due to pressure differences. The recent accident where Davy got pulled in, that was also a pressure incident. Because the water, it was in a wider area, and then it was narrowing down to the pipe, right? So when it is narrowing down, what happens is the pressure in that opening is far too less compared to the pressure where he was. So that pressure difference is what kind of drives him with an extra force. It's not going with the water, it's like extra. And then once you are close to that, you cannot control that. You'll be sucked in. So it's a kind of weird thing. I don't know why they don't put some kind of a, protection. Some steel bars going like that. Why can't they do that? It's pretty dangerous to have such things, especially in the backyard. I don't understand why they can't protect. Because pets can go in and all that. So many things can happen. Yeah.
Does a northward velocity mean you're just traveling north?
Northward velocity?
Yeah.
Yeah, you're going north. Right, we'll come to it one by one. Let's come back. Let's come back to our stuff. So did you understand this part? At the top, what is the velocity? What is the acceleration at the top? Negative 9.81. So acceleration is always going to be, so the velocity turns 0 at that moment, but the acceleration is not 0, it is still there. Okay. This line also can be understood for a car the same way. A car moving at a certain velocity in the positive direction, see, positive direction. A car is moving in the positive direction and you are applying, imagine you put your car in reverse, don't try that again. I'm just explaining this stuff. So if your car is on reverse gear when you are going at a higher speed or higher velocity, the car is eventually going to slow down and stop, but the reverse gear is still on, so it starts moving backward. And going faster and faster backward. It's going faster and faster backward, but it's negative, so it's still deceleration. So all through this journey, it's going to be deceleration. Now, can you draw one more graph? You understand this concept? Draw one more graph for this action. I have a ball. Okay? I have a ball and I drop it. I drop the ball. I drop the ball and the ball goes down and hits the table and comes back to half the height. The ball dropped from a certain height, goes down and hits the table and bounces to half the height. Can you draw a velocity time graph for it? Draw the velocity time graph.
Repeat it.
A ball dropped from rest. The ball is dropped from rest and it goes down, hits the whatever floor, and then bounces back to half the height.